AP Calculus BC, Unit 6 to A7, office hours, more for response practice with a variety of problems. Differential equation, axis below, 9 points. So I'd probably figure out where it's 0, which is going to be x equals 0 and y equals 0. So that's the 0, 0, 0, 0, 0, 0. Half of them done. 1, 1 is 1/2. Negative 1, 1 is negative 1/2. All right, hold on. Yeah, 1, 1, 1/2. I feel like I wrote the wrong thing on that picture. Okay. So this is going to be negative 1/2. 1, 2 would be slope of 1. Negative 1, 2 is slope of negative 1. 1, 3 would be a slope of up 3 over 2. 3 over 2. So there we go. That's your slope field. That's 1 point this time. 2 points. 6 points. While y equals fx is a particular solution to the given, let it be a particular solution with initial condition f0, 3. Use Euler's method starting at x equals 0 with a step size of 0.1 to approximate f.02. Show the work that leads to your answer. So we've got to do Euler's method. Now, if you feel good about the table, you can, but if it's been like a month since you did it, really this is just repeated tangent lines. And usually they only ask for a couple steps. The table becomes less beneficial. So y minus y1 equals m times x minus x1. I'm just going to do kind of the more straightforward way first. So we have our derivative up there, dy dx. I'm going to rewrite it right here. So that's going to give us slopes over tangent lines, and we have an initial condition. F0 is 3. So that'll be our first slope intercept. So now we got to plug in 0, 3 into our differential equation, and we get 0 over 2 is 0. So the slope is 0. X minus, so we're starting at 0, 3, x minus 0. So this is going to be x equals 3 is the line no matter what x is. So that means that f of 0.1 is about 3. Just, it's a horizontal line. Kind of interesting. Now we use that point, we're going to make a new tangent line. Y minus 3 equals, we need to find the next derivative at 0.13. So you multiply them on top, you get 0.3 over 2, which is the same thing as 3/20ths. Or however you want to do it. I mean, this is a problem that you can use a graphing calculator on. It's going to be 0.15 x minus 0.1. So slope intercept form would be 0.1x plus 3.015. Okay, maybe pull this off without a graphing calculator. So then we're going to plug 0.2 in. And let's see. Okay. I'm just trying to make sure I do this right. Okay, so we're going to plug in, I don't know, let's try it out. 0.2, I feel like I'm getting the wrong answer here. I don't know. I mean, according to this, you would get we'll check our answer in a second. This would be 0. You get 30, but you gotta move the decimal over. So I'm gonna get 3.045. Let's try the table. So the table is based off the same idea: y equals y old, y prime old, x minus x old. You can call this new. So y new equals y old plus y prime old times delta x. And in this scenario, so we keep track of the x's and y's and y prime, and then delta x. And delta x is 0.1 this time. We're starting at 0.3, and then we're going to 0.1, then we're going to 0.2. So the table is going to be real short. It's not as beneficial. So the new one is going to be this plus that times that. So we got to find the derivative to be 0. So we do this plus this times this. So you get 3. Then you got to find the next one. Next one is going to be these multiplied. 0.3 divided by 2 is 0.15. Right? So we are going to add that, plus that, plus that. And we get 3.015. So f of 0.2 is approximately 3.015. And what did I do wrong over here? It's something wrong. I don't know. Oh, this is going to be minus 0.015. So this should be 2.985. 2.985. 2.985. If you add 0.03 to this, you get 3.015. So you add 2.985, add 0.03, get 5, 1, add it to that, 10, carry it. There we go. So, little mistake. So either one of these ways, but okay, C. I mean, on fair response, I'd probably be tempted to do it this way because this whole shortcut thing, I don't know if that's like a super technical explanation. Fair response, you really want to be able to show the work and show it in a way that makes sense. Find the particular solution to the given differential equation. So now we're being asked to solve the differential equation. And we have an initial condition of f0 equals 3. And this says use your solution to find f.02. So find the exact answer after you solve it. Interesting. So we're going to separate the variable, integrate both sides. Plug initial condition in. Rewrite it. Exponentiate both sides. Get rid of the absolute value. We used rules of exponents right here. Let's break that up. Decide if it's positive or negative. It's got to be positive. Plug 0 in to get it positive 3. And we should also state the Should also state the domain. I think I made a mistake. Forget the x right here. X squared over 2, 1/4, 0 squared. That still comes out the same, but that should be 1/4 x squared. This should be 1/4 x squared, 1/4 x squared. So y equals 3e to the 1/4 x squared. The domain, no issues here, no issues there. So for the domain, negative infinity, positive infinity. Then we're supposed to actually find the exact value. I mean, I guess, find the exact value of 0.2. So we're just going to plug it in. 3e to the 1/4 times 1/5 squared. I'm just trying to get a nice answer without having to use my calculator. So that's going to be 1/25, 100th. On your calculator, it'd be 3.030. There you go. Which is pretty close to that estimate. Not bad. Not bad. Okay. Okay. After the function, initial condition, derivative, write the equation of the tangent line and use it to approximate 3.1. So this is like a Calc AB problem. One step tangent line approximation. So write the equation of the tangent line. It's going to be y minus 6 equals, I guess we should calculate f prime first. F prime at x equals 3 equals 1 plus e to the third over 3 squared equals 1 plus e to the third over 9. And so that's your slope. And so then your equation would be y minus 6 equals 1 plus e to the third over 9 x minus 3. So that's the equation of a tangent line. That's good enough. And we're going to use it to estimate f of 3.1. So, I mean, you could distribute this and then plug 3.1 in. Now, I guess this is where a calculator could come in. I mean, technically, on free response questions, you can just leave it unsimplified. Like this would be okay. So, either way. On a calculator, let's see what it gives us, just to make sure. So it's going to be parentheses 1 plus e to the third, close, divided by 9 times 3.1 minus parentheses 1 plus e to the third, close, divided by 3 plus 6. That's what you get. 6.234. Round truncated comes out the same. All right. So that's what we did in Calc B, AB. B says use Euler's method starting at x equals 3 and steps out at 0.05 to approximate 3.1. So it's only going to be 2 steps. Use F double prime to explain why this approximation is less than the actual value. So I don't know if you guys remember tangent line approximations. It has to do with concavity. If it's concave down, it's it's an overestimate. It's higher than the actual value. If it's concave up, the tangent line is always below it, and it's an underestimate wherever you use it. So that's really what it's going to boil down to. But maybe convincing that the second derivative is that all the time might be harder. So there's two ways we could do this. We could do y minus, so we're starting at x equals 3, so y minus 6. So we should find the derivative first at 3, just like we did this part. Actually get the same exact thing. So we're actually going to get the same tangent line equation. Y minus 6 equals 1 plus e to the third over 9, x minus 3, y equals 1 plus e to the third over 9, x minus 1 plus e to the third over 3 plus 6. But we're going to do 3.05. So as an approximation. So we can put that in our calculator. I can just use what we did last time and replace this with a 0, 5, and okay, yep. So that's going to be 6.117141872. I'm going to carry extra decimals. I'm going to use this for, I don't want to plug this into the derivative. That's just crazy. So that's our approximation. So then we're going to go to, we need to find the derivative at the last value. And I'm just going to write it as a decimal. Well, whatever. It is 1 plus e to the 3.05 over 3.05 squared. Okay, so the equation of the tangent is going to be y minus 6.117141872 equals 1 plus e to the 3.05 over 3.05 squared times x minus 3.05. So that's the equation of tangent line. And so then f prime of 3.1 is going to go there. So you're going to add this to the other side. That's ugly. Okay, let's see if we can do this. Parentheses 1 plus e to the 3.05. Close, close, divided by parentheses 3.05 squared, close. Time, this is where the 3.1 is going to go, times 0.05 delta x plus 6.1171411872. And we get 6.236. So there you go. That was kind of messy. Doing the table, I don't know. X, y, y prime, delta x. You're starting at 3 comma 6. You're going 3.05. And you're going 3.1. Delta x is 0.05 each time. It's going to be this plus this times this. So y prime in the first one is 1 plus e to the third over 9. It's going to be that plus that times that, which gives you a decimal 6.1171411872. The next derivative is going to be 1 plus e to the 3.05 over 3.05 squared. So it's going to be this plus that times that is going to give you 6.236. So it's the same work. I guess maybe it's a little better. Okay. Now we're not done yet. It says use the second derivative to explain why this approximation is less than 3.1. So we got to figure out what is it concave. It's got to be concave up the whole time between these points, or concave down the whole time between these points. So we got to find the second derivative ourselves, and so it's going to be low d high minus high d low all over low squared. Okay. So that's going to be x squared e to the x minus 2x minus 2x e to the x all over x to the fourth. We could factor an x out of everything. So it's e to the x minus 2 e to the x over x cubed. Okay. And so we need to, you can't just plug in 3.1 and say that it's positive, there. What we need to realize is this is the hard part, for x greater than or equal to 3, what's going to happen here? Add x equal. So maybe we could graph this and see what happens. Let's see. Parentheses e to the x minus 2 e to the x close divided by x to the third. Window, looking at 3 to 3.1 is all that really matters. We could say like 3 to 10, and let's just try this. So there's a graph. It's negative down here. Did I do something wrong? Okay. If x equals 3, you're going to get e to the third minus 2 e to the third over 3 cubed. And that's 1 e to the third minus 2. That's going to be negative 2 minus 1 e to the third, which seems negative. So it seems like it's going to be, and then if you plug even bigger numbers in, it's still going to end up being negative. I feel like it's always going to be negative. For x is greater than 3, I think f double prime of x is going to be negative, concave down. This is contradicting my answer, so I don't know if there's. Let's take a quick look. So I guess they did a little. Let's see. They did a little manipulation here. They could say, okay, well, there should still be an x here. Well, that makes things different. There should still be an x there. And so they factored an x minus 2 out of the e to the x terms. Okay, and so they're saying if x is greater than 3, then this is going to be positive, right? and e to the third is definitely bigger than 2. And for any other x bigger, this term is just going to be bigger. So when x is greater than or equal to 3, then this is going to be greater than e to the x minus 2 over x cubed is going to be greater than 0. So therefore it is concave up. I think this is hard. So our answer is going to be the graph of f of x is concave up for x greater than or equal to 3. Therefore, the Euler approximation must be an underestimate. Concave up, tangent lines below, it's an underestimate. So proving that derivative, that was just kind of weird. Okay, C says 3 to 3.1 of f prime of x. Use this to find f of 3.1. So this is just good old-fashioned fundamental theorem of calculus part 1. So if you integrate a derivative, you get the original function, plug the limits in, right? And so we want to find f of 3.1. Well, that's going to equal f of 3 plus the integral of 3 to 3.1 f prime of x dx. And f of 3 was known, that was 6. And we can do this on our calculator. And this is an exact answer. I mean, this is not approximation technique. So our calculator, I'm going to do 6 plus math 9. And I'm going to do parentheses 1 plus e to the x, close parentheses, divided by parentheses x squared, close parentheses, comma x, comma 3, comma 3.1, enter. And that's the answer. 6.237 truncated, or 6.238 rounded. And this will kind of verify, was our estimate up here? Wow, it was really close, but it was under. It was an underestimate, barely. Okay. That was fun. Okay, next one. Consider differential equation. And the x-degree sketch to a slow field at 11 points. There's one missing there and there, probably for good reason. Maybe, maybe not. So when does this equal 0? Well, when x equals 0 and y equals 1. So 0, 0, 0, 0, 0, 0, 0. We just got 7 of 11 points. That's nice. 1, 0 is going to be positive 1. Negative 1, 0 is going to be negative 1. 2, 0 is going to be positive 2. Negative 2, 0 is going to be negative 2. 1, negative 1 is going to be positive 4. And negative 1 is going to be negative 1 times negative 2 squared is 4 is negative 4. So there you go. There's your slope field, 2 points. It says B uses the slope field for the given differential equation. Explain why a solution could not have the graph shown above. Why couldn't this have that? Well, because there's this horizontal line right there that this does not have. It has to have this horizontal asymptote. So something along those lines, B, the graph does not have a slope of 0 when y equals 1. I mean, that's kind of the easy thing to point out. That's clearly wrong with it. C, find the particular solution to the given differential equation with the initial condition. Okay, so separate the variables. I'm going to rewrite it as y minus 1 to the negative 2. Power rule, bump it up 1, divide by the new exponent, plus c. I'm going to rewrite this a little nicer. Let's find the initial condition. They told us 0, negative 1, so we're going to plug a negative 1 in for y, 0 in for x. So c equals positive 1/2. So we're going to rewrite it. Negative 1 over y minus 1 equals x squared over 2 plus 1/2. I want to combine these into a single fraction, so I can just flip both sides upside down and then multiply by a negative. And then add a 1 to both sides. Now we got to check out the domain. Can't divide by 0, which can't even happen. You get imaginary. The original problem was totally okay. No issues there with x or y, causing that to be undefined. So the domain is going to be all reals. Negative infinity to positive infinity, single open interval. Okay. And then D says to find the range. Well, what are the possible y values of this? Maybe we could combine that. I'm just trying some different things here. So that's the same function. I mean, we could do some things as x goes to infinity. This is infinity over infinity. These are the dominant terms. It goes to 1. So it has a horizontal asymptote, y equals 1. So 1 somehow is going to be either the low or the high point of it. And then, I guess we could see if there's any relative maxes or mins, or I don't know. Is there, and that's horizontal asymptote, so it could cross it. It could look something like this. So it could really have no effect on it. You could find out if it crosses it by setting the equation equal to the asymptote and trying to solve for it. And we get something that doesn't make sense. So it doesn't cross it, which gives us a little bit of information. Now, let's see. So I mean, we could see if there are any critical points or anything. I mean, we could do y prime equals low d high minus high d low all over low squared. It's going to be 2x cubed plus 2x minus 2x cubed plus 2x. Those cancel each other out. You get 4x over x squared plus 1 squared. So this is y prime, and equals 0 undefined, x equals 0. So we can do a line check real quick. And then if you plug in x equals 1, it's positive, negative, so it's decreasing, increasing. This is a critical point. This is a relative min. So it might be interesting to calculate that. So if we plug 0 into our solution, we get -1. So that's a relative min. It's a valley, and then it goes towards, and it's the only one. And then it goes towards y equals +1 on both sides. So the range is -1 to +1. It does actually get to -1. It never gets to +1. I don't know. Maybe I made that harder than it was supposed to be. All right. Awesome. Okay. We have a function satisfying this derivative for all real numbers. Initial condition, they tell us that the limit goes to 0. It says to evaluate the integral of 1 to infinity of -x f of x dx. Show the work that leads to your answer. Okay, well, what you guys should realize is that -3x fx is the integral of f prime of x, right? Which means, and this is an improper integral, so we could say that this equals the limit as b goes to infinity. Now, I may have been you've been lazy like this on a test before and just write infinities, but this is the proper way, and this is free response, so you got to do it proper. So that's the proper way of writing that improper integral. And so, and that's going to equal the limit as b goes to infinity of the integer of f of x, f prime of x is f of x. So now they actually told us the limit as x goes to infinity of f of x. This right here is going to be 0. And then minus f of 1, whatever f of 1 is, which they actually told us it was 4. So the final answer is going to be -4. That was kind of fun. B says use Euler's method starting x equals 1 step 7.5 to approximate f of 2. So we're starting at f of 1, 4, delta x is 0.5. I'm trying to find f of 2. So this is 2 steps. So we could just, we could do, well, let's find the derivative at 1. And then you get f of 1, which is 4. And so then you get -12 is your slope. So y minus 4 equals negative 12 x minus 1. That's our tangent line. It's going to be negative 12x plus 12 plus 4. So y equals negative 12x plus 16. And we're going to use that to approximate 1.5. So if you plug 1.5 into this, you get negative 18 plus 16. F of 1.5 is approximately negative 2. Okay, let's do it again. So now f prime of 1.5 equals negative 3 times 1.5 times f of 1.5. And so that's going to be negative 4.5. Now f of 1.5, I guess we're going to just use our last approximation. So f of 1.5, and this is an approximation, I guess now, is positive 9. So y minus negative 2 equals 9, x minus 1.5, y equals 9x minus 13.5. What did I just put here? Minus oh yeah, negative 2. So it became plus 2. So we subtract 2. So y equals 9x minus 15.5. So f of 2 is approximately 9 times 2 minus 15.5 is 18 minus 15.5. F of 2 is approximately 2.5. So that is Euler's method. We could do the table if you want. I'm a little sketchy about doing this on a free response problem. Besides, if you feel confident in doing it or not. So we're starting at 1 comma 4, then we're going to 1.5, and then we're going to 2. Delta x is 0.5 each time. Don't need it for the last step. The derivative, we still got to do this work. It's going to be negative 3 times 1 times f of 1. So it's going to be negative 3 times f of 1 was 4, so it's going to be negative 12. And the new one's going to be the old y plus y prime times delta x. So it's going to be this plus that times that. So it's going to be negative 2. So then you have to do negative 3 times 1.5 of f of 1.5. And that's going to be negative 4.5. F of 1.5 is about negative 2. So that's going to be 9. So it's going to be this plus this times this. Negative 2 plus 4.5 is 2.5. I don't know. I feel safer just doing it this way. And it's, I don't know. Usually they only give you like 2 steps. They keep it simple. Because C says write and expression for y equals fx by solving the differential equation with initial condition. So good old solving the differential equation with an initial condition. Find the exact solution. So we have to separate the variables, integrate both sides, plus C, use the initial condition, define the C. So C equals natural log of 4 minus plus 3/2. So we rewrite natural log of the absolute value of y equals negative 3/2 x squared It's natural log of 4 plus 3 halves. Exponentiate both sides. Get rid of the plus or minus. This is going to give you a 4 in front. And then that'd be e to the negative 3x. 3 halves x squared plus 3 halves. We want to go with the positive. Plug 0 in. No, plug 1 in. E to 0 is 1. We want it to be positive. So now we got to just figure out what the derivative or what the domain is. So this is a negative exponent, which means it could, which means it'd be in the denominator. But e to any number is never going to be 0. So there's no fear there. Here, there's no issues. The domain is all real. It's negative infinity, infinity. You better put that domain with your answers. All right, there are a couple interesting problems in there.